So today we are going to discuss on some topics. Okay, so we are going to discuss firstly the anomalous behavior of beryllium. So anomalous means difference. Okay, why beryllium is different from the rest of the members of the same group. So beryllium, the first member of the group, shows anomalous behavior, or we can say properties, compared to the rest of the members. So unlike other members, okay, the first point, unlike other members, beryllium has very small atomic and ionic size. Okay, so because of this small atomic and ionic size, it shows the highest ionization enthalpy, okay, among the group, and it forms covalent, okay, compound, or it is highly covalent, and because of that it gets hydrolyzed, okay, in water. Now this ionization enthalpy, okay, ionization enthalpy will depend on the size of the atom, or we say element. Okay, so the closer an electron to the nucleus, there will be much more attraction between the nucleus and the electron. So smaller size means the electron will be closer, okay, and then if the electron is closer to the nucleus, it will require higher energy, and that energy is the ionization enthalpy, and because of that beryllium has the highest ionization enthalpy among the group, okay, and this ionization enthalpy will decrease down the group as the size increases, okay, and this beryllium, due to its small size, it can polarize a large anion, okay, so it polarizes, and after polarizing it will form a covalent bond, okay, so in this covalent bond electrons is shared. Okay, now let's come here. Point 2, beryllium does not exhibit coordination number more than 4, okay, coordination number more than 4, so it cannot have more than 4 coordination number. Okay, that means it will have up to 4 coordination number. That means it will have up to 4 bonds. Okay, Be can have up to 4 bonds. Okay, so it can be attached to any other species. Okay, the reason is due to the absence of d orbitals, or we say there is only 4 orbitals, okay, in beryllium. So in beryllium we see 1s2, 2s2. There is no d, okay, no d orbitals or even p, okay, and because of that it will form only up to 4, okay, so in these 4 electrons will involve. Now other members have coordination number. I've written in short form up to 6, okay, so other members, since they are bigger in size, they will have d orbitals, okay, and since they have d orbitals, their coordination number will increase, okay, and because of that they can have up to 6, okay, that means they can show up to 6 coordination or 6 bond. Unlike the oxides and hydroxides of other elements in the group, the oxide and hydroxides of beryllium are amphoteric in nature. This we have discussed in our previous videos also, okay, so the oxide and hydroxides of these elements, they are alkaline in nature, okay, that means basic, and because of that they are called alkaline earth metals, except for beryllium, because the oxide and hydroxide of this is amphoteric in nature. Now diagonal relationship, okay, so diagonal relationship is just a diagonal relationship in simple words, okay, so we see group 2 element, okay, beryllium, the next one is magnesium. Now then the next group, okay, to this group 2 is group 13. boron and aluminum. So the d of the d blocks elements, okay, are not included. Okay, so the next group next to this group 2 is 13, and then after that 14, 15, okay, and so on. Now this diagonal relationship is the relationship, okay, is a diagonal relationship, okay, between beryllium and aluminum. So this beryllium shows similar properties with aluminum, okay. However, there won't be any diagonal relationship between this boron and magnesium, okay. So the next element, this boron will show diagonal relationship to the second element of the next group, okay, and so on, okay, in periodic table. So this relationship or diagonal relationship is known as just diagonal relationship, okay, in periodic table. So why they show this diagonal relationship is because of their size, okay, because of the size of the ions, okay. So Be2 plus ions, okay, and Al3 plus ions, they have similar, okay, or almost same charge to radius ratio of 31 picometer, okay. So that is the reason why beryllium resemble, okay, aluminum in some ways. Some similarities are, okay, like aluminum, beryllium is not readily attacked by acids, okay, I'm writing in short form acids, due to the presence of oxide film on surface of metal. So this beryllium metal, okay, in presence of oxygen, this oxide layer is formed, okay. This oxide layer or film is formed, okay, and this film acts as a protective layer against the acid, okay, against the attack of acid. So the any acids, they are unable to directly attack this beryllium, okay, because of this protective layer, and it takes time to attack this beryllium, okay. So in the same way, aluminum show this oxide film, okay, and both are not readily attacked by acids. Beryllium hydroxide dissolve in excess of alkali to give a berylate ions, okay. So in the excess of alkali or alkali solution, okay, it forms this beryllium hydroxide, it forms berylate ions, okay, BeOH4. See, notice here, it will form up to 4 bonds, okay. So that means 4OH will be here, okay. Okay, like we have discussed, it have coordination number 4, so 4 bonds, up to 4 bonds. However, aluminums, it can have up to 6 also, okay. But in here, this aluminum hydroxide gives aluminate ion, okay, AlOH4 minus. The chlorides of both beryllium and aluminum have chloro-bridge structure in vapor phase, okay. So they both show chloro-bridge structure, okay. So that means chlorides means BeCl2 AlCl3. So BeCl Cl, okay. So this will show chloro-bridge structure, okay, like this, okay. And now aluminum, even aluminum will show. Okay, chloro-bridge structure, and that also in vapor phase. So both show this structure in vapor phase. Now chlorides of both aluminum and this beryllium, they are soluble in organic solvents, okay, and they act as strong Lewis acids. So according to Lewis acids, okay, sorry, Lewis concept, acids are those that accept electrons, okay, and base means donate electrons, okay. So in this case, BeCl2 2. Okay, this one BeCl2. Okay, the Lewis dot structure will be like this. Okay, so this dot denote the electron. Okay, so there are 4 electrons involved, and if you come across this octet, okay, to form a complete octet they will need 4 more electrons. Okay, and because of that they will have tendency to accept electrons. Okay, and because of this reason, since they tend to accept electrons, they are strong Lewis acid. Now AlCl3. Okay, so structure will be AlCl. Okay, Cl. Okay, so 1 2 3 4 5 6 electrons involved. Okay, so it requires only 2 electrons. Okay, so because of this, okay, they are known as Lewis acids. Okay, so base means they can donate this long pair of electron. Okay, this pair of electrons to these acids. Okay, example can be this water. Okay, it has 2 lone pair, or ammonia having 1 lone pair. Okay, we come to our next point, next topic, calcium hydroxide. Okay, so this comes under proton compound of calcium. Okay, and some topics were deleted, so we are going to discuss only only those which are included. Calcium hydroxide, known as slaked lime. Okay, so chemical formula is CaOH2. So this calcium hydroxide is prepared by adding water to quicklime or calcium oxide. Okay, quicklime, addition of water, and then we get calcium hydroxide. So this calcium hydroxide or slaked lime is white amorphous powder. Okay, and they are sparingly soluble in water. The aqueous solution of this is known as lime water. So the aqueous solution, okay, when we mix this in water, okay, we'll get a solution. Okay, that solution will give you lime water. Now suspension of this slaked lime in water, suspension of this, okay, it's known as milk of lime. Okay, as it looks like milk. Okay, white in color. Now when excess carbon dioxide is when carbon dioxide is passed through this lime water, it turns milky. Okay, like a milk color. Okay, and why it turns milky color? Because it forms calcium carbonate. Okay, so this lime water react with carbon dioxide, okay, to give calcium carbonate. Okay, so this one is precipitated. I'm writing in short form. Okay, precipitate. Okay, the spelling is like this: precipitate, and we get water molecule. Now when we pass excess CO2, okay, in this, okay, this precipitate will dissolve. Okay, it dissolves to form calcium hydrogen carbonate. Okay, so this precipitate calcium carbonate is when we pass this excess carbon dioxide, okay, we get calcium hydrogen carbonate. Milk of lime react with chlorine to form hypochlorite, a constituent of bleaching powder. So this milk of lime, okay, this suspension of lime in water, we call it as milk of lime, react with chlorine to give calcium chloride plus this constituent of bleaching powder, okay, known as hypochlorite. Okay, this is hypochlorite and water molecule. So the reason I wrote all this down is to save time. Okay, if you write all these down and explain, it will take long time to complete it. The next topic is calcium sulfate, known as plaster of Paris. Chemical formula is CaSO4 have water, okay, or it is also known as hemihydrate. Okay, so hemihydrate of calcium sulfate, okay, is known as plaster of Paris. Okay, we call it as plaster of Paris. So this hemihydrate calcium sulfate is obtained when this gypsum, okay, calcium sulfate is heated to 393 Kelvin. So when we heat this calcium sulfate, it loses, okay, water, okay, this water is evaporated, okay, some of it is evaporated, and we get this one, okay, when we heat this one, okay, we get this one, calcium sulfate and water molecule. So this should be carried out at 393 Kelvin, okay, and if we heat it above this Kelvin, this water gets removed or evaporated, and you will be left with only CaSO4, calcium sulfate, okay. And when we are left with no water, okay, no water of crystallization, that means this is evaporated, this is no more, okay, we get anhydrous CaSO4, okay. So this is called as anhydrous because no water of crystallization is present, okay. So when there is no water of crystallization present, we call it anhydrous, okay. So this anhydrous CaSO4 with no water of crystallization is known as dead burn plaster, okay. So it has remarkable property of setting with water. So when we mix it with water, it setting take place, okay. So setting take place and it forms a plastic mass, okay, when mixed with water. So the duration is 5 to 15 minutes, okay. So within 5 to 15 minutes it's turned into a hard solid. Now let's see some uses. Some uses of it are, say, it is largely used in building industry and as well as plasters, okay. Now it is used for immobilizing the affected part of organ, whether it is bone fracture or sprain, okay. So we use this plaster of Paris, okay, usually to immobilize the part, okay, the affected part, okay, where bone is fractured, okay. So in order to heal the fractured bone, okay. Now it is also used in dentistry, okay, employed in this dentistry and ornamental work and making of statues. Now our next topic is cement. So we all know what is cement, okay. Cement is an important building material, okay, building material, important, I wrote in short form. So this cement was first introduced by England, okay, this Joseph S. Dean, 1824. So this cement is also known as Portland cement, okay, because it resembles the limestone, this natural limestone of Portland in England. Now let's come here. So this cement, we can obtain this cement by mixing or combining calcium oxide, okay, or materials containing this calcium oxide with clay, okay. This clay containing silica, okay, SiO2, along with these oxides of aluminum, iron and Mg, okay. That means these oxides, okay, aluminum oxide, iron oxide, magnesium oxide. Now average composition of cement. So the average composition of cement is calcium oxide, okay. So calcium oxide with the highest composition, 50 to 60%, silica 20 to 25%, aluminum oxide 5 to 10%, magnesium oxide 2 to 3%, iron oxide 1 to 2%, sulfur dioxide 1 to 2%. Now in order to get a good quality cement, okay, there is some specific ratio, okay. So the ratio of silica to alumina, okay, should be between 2.5 to 4. Okay, and ratio of lime, okay, this lime aqueous solution of calcium oxide to the total oxides of, so all together this one, okay, oxides of silicon, aluminum, iron. So these are the oxides, okay. This and this total should be close to 2. Okay, ratio should be close to 2. Now raw materials. Okay, what are the raw materials for manufacturing of cement? So there are 2 raw materials, mainly limestone and clay. Okay, so this limestone and clay, so this limestone and clay are mixed and heated. Okay, after heating they are fused. Okay, they get fused together and react. Okay, so when they react they forms this cement clinker. Okay, and this cement clinker is mixed with 2 to 3% of gypsum. Okay, chemical formula is here, and when it is mixed with 2 to 3% of gypsum, cement is formed. The important ingredients present in Portland cement. So these are the important ingredients present in cement. The first one is dicalcium silicate. So di, you know, 2, so Ca2Si4, so it will be in 26%. Okay, tricalcium silicate, tri means 3, so Ca3SiO5, okay, 51%. Tricalcium aluminate, Ca3Al2O6, okay, 11%. So one more thing, this cement, okay, it does not have a very defined composition. Okay, so the composition this cement may vary. Okay, like it may be between 50 to 60 or between 20 to 25. Okay, any percentage, okay, between this. Okay, setting of cement, okay, we all know this. Okay, when we mix it with water, this setting of cement takes place. Okay, we all know that. Okay, so the reason is due to hydration of the molecules of the constituents and their rearrangements. So hydration takes place, okay, and cement, setting of cement takes place as a result. So this hydration we have discussed before also. Okay, we won't discuss much into detail about this now. Very important one, this gypsum. Okay, we all know. Okay, you might have discussed in your class 10 standard also this one. So gypsum is added to cement to slow down the setting process. Okay, so gypsum is added, okay, in order to prevent the fast setting of cement.